So I'm going to talk a little bit about Kinect, the key thing that Kinect does from our point of view, the computer vision problem in Kinect, which is tracking your body motion. And I'm going to show you sort of how the kind of research we do at Microsoft Research ended up with us being able to help the Kinect guys, even though we approached it from a very different angle, and that's where the sheep will come in. So, for a long time, people who do computer vision have been interested in the idea of tracking the human body. So about 10 years ago, the head of our lab, Andrew Blake, was interested in analyzing motions like this ballet dancer. And in those days, what he's showing with his red outlines is basically that in each frame of the video, he's identified one of a few standard poses of the body. So you can imagine maybe building a dance game based on this sort of technology. But we wanted to move slightly further. We want to not just recognize one of a set of standard poses, but to solve the problem of taking an image like this one and converting it into a 3D model which is in the same pose. We use pose to mean the sort of the joint configuration as the object represented in the image. So if we got that working, and this is around 2005 when lots of people in the computer vision community and research were trying to solve this problem, so you can see that it's taken this input image and sort of completely independently in every frame, it's trying to figure out what the guy is doing. It's not bad. You titter, right? But this is a very, very hard problem. There are all the problems with all the colors, and you've only got one camera viewpoint. But I'm going to spend a little while, a few minutes, talking about how we go about solving this sort of problem in computer vision with the aid of machine learning. So, first of all, let me state what the problem is. What do I actually want to solve? Well, I want to take this image, and for the moment I'm just calling it Z. Think of Z as, a million numbers, all the RGB values in all the pixels of the image. And what I want to output is a set of joint angles. So for I have a sort of a model of how the human skeleton is constructed, and I would like to give me a list of the angles of every joint in the body. So elbow 1 angle, shoulder 2 angles, saying where it is. Head position is represented by angles. So I want to take the million numbers in this image and output, let's say, 40 numbers, which are the positions of all the angles that we care about. That number can go up or down depending on whether you do fingers and how much detail you do for the face. But let's say, 40 numbers representing the angles. So that's my job, image in, angles out. Okay, I'm not really going to be able to deal with this image. It's far too complicated. And a lot of it is irrelevant, right? I don't really need to understand houses and sky in order to track the pose. In research, we were interested in simplifying the problem so much that we decided all that we would take from this image is the outline of the person. So we take this image, which is some millions of numbers, we convert it into a new representation. It's still hundreds of thousands of numbers, but each pixel is now on or off, inside or outside the object. And Chris showed you earlier how you can do that with llamas. I assure you it extends to humans. So the goal is image, silhouette, angles, 3D rendering. And then let's just look at those terrible results again, but now you can see that it's producing this output based only on this silhouette. So in fact, it's a fairly tricky problem, and maybe you're surprised that it gets it as right as it does. I'll show you how it does that. I said this was millions of numbers. This is, a few 100,000 numbers. We want to do even better than that, right? We can't really deal with all these hundreds of thousands of numbers for every single frame of video that we see. So what we do is we take this image, and we try to convert it into an even smaller number of numbers. Who knows what a vector is? Great, okay. So what we do is we take this image and convert it to a vector in n-dimensional space. And that may sound like a complicated thing to do, but what we do is actually pretty simple. And in fact, you're going to help me do it. Okay. So what I said was I have a vector of numbers, and this vector of numbers contains elements z1, z2, down to zn. And these just contains things that you could measure looking at these images. So one thing I can measure, just looking at this image on the left, is the number of pixels that have value white. And I'm going to call that the area, okay, of the thing represented in this image. Can you think of some other number I might be able to compute? Height, yes, so I could measure the distance from the topmost to the bottommost pixel. I could think of some other numbers, Z3 equals, so here you can see I've done an edge detection. I could count the number of pixels in here and call that perimeter. Ooh, with terrible writing. So what I'm saying is we can think of some stuff. We can analyze this image. Now, none of you believe that any one of these numbers on its own is going to be able to tell you the angle of the elbow. But if we collect enough of these numbers, we should be able to build a system that can work out elbow angles for us. So what we're trying to do is build a magic function, which I'm going to call f, which takes the vector of numbers z and turns it into the vector of joint angles theta. And building f, you can think of as one of the jobs of machine learning. How do I build f? Well, the first thing I do is I start with lots of examples. So I gather silhouettes for lots of different parts of this golf swing. And for each of these silhouettes, I compute my vector of numbers z. So here I've done 3 numbers. Let's pretend it's area, perimeter, height. And I also record for each of these images what the angles were. So this is quite a tedious process. I have to place the 3D model manually adjusted so that it matches the image. And then I can read off the theta values. And now I have a set of inputs that I can get from any image and the outputs that I would like to produce. Given these z's, I would like to produce these thetas. As Simon Peyton-Jones said earlier, the way that we deal with these difficult problems as computer scientists is to abstract them out. And the abstraction we use here is the idea of relationships between points in some space. So although I said, height is not going to predict, or area is not going to predict elbow angle, let's pretend for a minute that one number in is good enough to predict one number out. So the thing I'm looking for on the output side here, theta, is elbow angle. And let's pretend that the number I'm putting in here is height. And what I do is I gather all those training images, and for each training image, I represent each of those images by a single dot. That says, in this image, the height was whatever, 2.3, and, sorry, the height was 3, and the elbow angle in that case was 2.3. And what you can see is, if you use something slightly cleverer than height, you can get a relationship which is represented by these dots. So now, if a new image came in, so this is a new image that we haven't seen before, the silhouette, I'm calling it Z new, by which I mean just the vector of numbers, not really the image. I can look up in this list, I could say, give me the closest point in this collection to the image I've got, and then just print out whatever the joint angles were for that, and then we get a picture like this. Now, I might get a very similar image, very close to the one that I got, but because of the noise on this data is noisy, the relationship between height and elbow angle isn't that great. If I have 2 very similar input images, I might get quite a different answer on the output side. So a natural thing you might want to do is to think of some simple representation of these dots. Okay, so I would say, I don't want to just store all the dots and look up the nearest one every time I get a new pose. What I might want to do is get a simple representation of this. So for example, I might say this curve, it looks a little bit like a sine wave. Would you agree? So I might say, I don't need to do any looking up. I might say f of z equals sine of z. Now you're saying to me that's nonsense, right? Because sine looks like this. Right? And this one's sloping slightly upwards. And anyway, it's offset a bit. But if I add a little bit of this, y equals ax, az, plus a constant, I'm going to get a function which looks a little bit like that one. What machine learning would do, or one way, and you'll get the proper explanation in a minute, but this is a very old idea called fitting of functions. The computer's job is given a batch of little functions, sine of z, z, and it's supposed to find out these numbers a and c that describe the data. What's cool about it, I had hundreds of data points, and really now I'm left with only 1, 2 numbers describing the whole relationship. And if I have that function, then I can stick in my new z, read off the new theta, and everything runs really fast. So that's great. And if I do a nearby z, it works really well. But as Chris was telling you, the world isn't exact like that. And in fact, the relationship between height and elbow angle is pretty rubbish. So when I put in the new image z, I don't want to get an exact answer back saying this is the pose. What I want to get back is something that says, it could be anything, right? But it's definitely not up here. That's got low probability. Definitely not down here. That's got high probability. So what this probability distribution is really saying, your answer is somewhere in here and it's most likely around there. Okay? Now, if you want to act right now on this output, if you want to print the avatar's position, you've kind of got no option other than to pick an answer around here. But let me show you why this is going to help. Why it's going to help is the problem is harder than I say. It's not just that the height is a noisy measurement of elbow position. It's that the same input image could give you two different body positions. So because of image noise, even though there's a little bit of hand sticking out here, look at both of these poses. They're sort of both plausible interpretations of this silhouette data, accounting for image noise. So what we want is a function that doesn't give you one answer when you stick in Z. It must give you multiple answers. It must have some way of representing this multimodal uncertainty. So what the function is going to do is, instead of spitting out a probability distribution with just one lump like a Gaussian, it's going to spit out a probability distribution which represents the multiple possibilities that this image could have. Again, maybe that's not very handy. You might just think, take the most likely one. Okay? But we'll get to that in a second. So I gave you this, a collection of points. That collection of points was not the true story, because when I had that collection of points, any Z gave a single theta up to noise. Now what happens is if I go for Z here, I'm going to get multiple answers. So what I'm going to do is print out a probability distribution saying, if this is the input image, these are the two possibilities for elbow. And what I'm going to represent is no longer this function y equals sine x or whatever it is, but a two-dimensional function which describes the probability density of the training that I got. So I'm now talking in terms of probabilities, not in terms of rules, y equals sine x. When I have this representation, this two-dimensional representation, I can put in a new image and it says, don't know, that's an ambiguous pose, right? Because we can't see the arms, they could be doing anything. I can put in another new image and it says, well, that's a slightly less ambiguous pose. Here are the two possible answers. And then finally, I might get an image which is pretty clear. So if your arms are up here and it's a golf stroke, you know, that's unambiguous. This is useful because now when I want to interpret what happened in the past, or conversely, if I run the sequence in reverse, if I start in an ambiguous pose and end up in an unambiguous pose, I can be fairly sure that this was the trajectory that got me there. I can remove the ambiguity. That doesn't seem very useful. Why do you care what the system thought 3 frames ago? But now imagine running it in reverse. I start here in an unambiguous pose. The system moves into a position of ambiguity, but I can still do a combination of where I was and how likely it is to have moved to there or there, so that when I get to the very ambiguous pose, I still have the right answer. Okay, so that's one nice bit of story. I'll just tell you one more problem. I showed you that we had this. This is the training examples represented as points in space. And, you know, it all looks very nice and we could fit a function to it. But in fact, we don't get that. This is typically what you get. Why? Because it's actually pretty expensive, the way we did it back then, to label each of the input images with where all the joint angles were. And we're living in a very high-dimensional space, so points are rare. When you have this situation, there's one more trick we can use. This is the model that the system will tell you happened, given those points. It can't guess anything else, right? I mean, why should it believe that there's a funny S shape? All it can see are these points. It will pick a picture like this. Yeah. And the problem is we don't have enough data. There's a cool trick we can use. Remember I said it was difficult to label each of the images with the poses. But what's actually easy to obtain is more images. Okay, so I can record lots of images. I just can't be bothered labeling them up with the poses. And it's also easy to obtain more poses. I put on those funny suits. Have you seen these suits with silver, you wear silver markers and it records your motion? Has anyone seen this? Yeah, a few people. So from those funny suits, I can record lots and lots of angles, but without the images. And then because of the way we can deal with this probabilistically, we can say, this picture does not explain the images that I collected. Remember, the images are kind of dense here, and there are hardly any out here, whereas the poses are fairly equal. This picture doesn't explain those images because it's not sufficiently dense here. So by combining the information, it kind of feels like magic, right? Because the images had no information, the poses had no information, we just had a few dots linking us together. But we can just combine that information probabilistically, and suddenly, magically, it gives the right answer, because the only way to get a line from here through here to here, while obeying this projection, is to curl it into a little s. So this is a trick we use to make the most of data. Now, as Chris says, in the world of the future, there'll be so much data we don't know what to do with. But you will always have problems hard enough that the training data you have available just doesn't do the job. So we did all that, and now we have slightly better results. So this is us in 2007, and here's a sequence, the input sequence. This is all that the computer sees, this silhouette. And this is our depiction of what happens, what the person is doing. So it's good in a few ways. It's quite stable because we did this sort of backward chaining thing to make the most probabilistic answer. He's locked at the hips, so don't be surprised when his jumping seems a bit odd. But you can see that basically, until the motion gets too fast, we're following pretty well a pretty wide range of motions. And that was the state of the art in October 2007 in human body tracking. So, we worked on more at that. We got it a bit better. And then in September 2008, some Xbox folks said, we understand there's all this work on body tracking. We know some people here have done body tracking. Can you do that for us? And we said, no, because, it really has to work. Right? It has to be not just a video of a man, doing some exercises. It must work for all motions, for all sizes and shapes of people, for people with fast motion, slow motion. And we used to always think that real time, which is, 30 frames a second computation, was the holy grail of high-speed computing. Not on the Xbox. Because the Xbox is busy doing lots of work with rendering computer graphics, doing game AI, doing a bunch of other stuff. So we were told we could have 10% of the Xbox in order to do this computation. So the code that used to take 1 minute per frame now has to run at about 300 frames a minute. It needs a 10,000-fold increase in speed. And of course, it must work for multiple people in the scene. So, we thought, we can save you lots of money. It's just not going to work. Don't do it. But they had a trick. And the trick was they had a 3D camera. So the 3D camera meant that instead of having to worry about the silhouette and the colors and so on, we got a sequence of images like this. So dark-colored pixels are close to you, and light-colored pixels are far away. Or viewing it another way, this is a set of three-dimensional points representing this person's motion. So this camera provides much more detailed information than that single silhouette that we got from the 2D camera. Still looked pretty nasty to do it. So what do we do? Well, we know about machine learning. We know the first thing you do when you've got a machine learning problem, long before you know how you're going to solve it, is you collect training data. We used to collect training data by taking images and manually clicking on them to say where the angles were. These people have a pretty big budget. So they immediately set up teams which visited 10 households across the globe of different sizes and shapes, brought the camera there and just videoed the people saying, pretend you're playing the game. So they told them to do motions for the game. We didn't know what the games were going to be, but they said just do typical motions. And they took that data and labeled it up to be our test data. At the same time, one of the other reasons, you might say, why couldn't we have used computer graphics to generate our test data for the training? And we could have, but to do a realistic computer graphics rendering of all the poses and all the conditions that we wanted would have required the resources of a Hollywood studio, so obviously we weren't going to do it. And of course, when you say that to the Xbox people, they say they just ring up Hollywood studios until they find someone who'll do it for them. So they generated billions of computer-generated images for us. And at the same time, we were still thinking about how, okay, we know the training data is coming in, so this is good news, but we still don't know how we're going to actually solve it. So we were sitting wondering how to solve it. At the same time, Jamie Chaton, who's an author on this paper, has been working on a quite different problem. Jamie, along with many people in computer vision over the last decade, say, or last 7 years, about 7 years ago in computer vision, we suddenly became bold and thought, I think we can recognize objects like sheep and cows and people and sky. So Jamie and friends built a set of 20 object categories, which are represented down here, and built systems which could look at any image and just decide what the various objects in the image were. And, you know, it gets it right a lot of the time. 80%, 90% of pixels might be right. So here, this is very good. In this case, they've got the human, but the body includes some extra stuff over here. You know, the road goes into the trees. But mostly, they can do this right. So that's what Jamie was good at. And something else they were good at was doing this fast. So this was a video they made for a conference, again, around this time, around 2007, 2008. So in this video, they're going to say, we're going to do real-time recognition of objects. They didn't actually bother to take the webcam and the computer out to the field. So what they've done is they've put a video on screen, and then they're videoing the video with the webcam. And what the system does is takes each input video frame and just labels the objects in the video. And as you can see, it does a fairly consistent job of distinguishing grass from sheep, even if you rotate the camera, or in a minute we'll see a little bit of sheep coming in. So even a partial sheep is recognized, largely because of properties like the color, the texture. What's surprising about this is how well those properties work when combined with the kind of probabilistic reasoning that we've been learning how to do over the past few decades. So that's pretty good. It can do lots and lots of different things. I can show you the video later if you like. So what did Jamie do? So Jamie thought, okay, I'm very good at object recognition very fast. I don't know much about human body recognition or pose recognition. That's kind of a different problem. But I know I'm going to turn the human body recognition problem into an object recognition problem. And this was a sort of really clever idea. So what he said was, okay, I'm going to divide the human body into little pieces. Hands, 32 different categories of object. And a category of object is hand, forearm. Well, you can see them here. Okay, the head, top left corner of head, top right corner of head, etc. And he's going to build a system, so now his training data, his Zs are these depth images here. His thetas are these output colored maps. So he wants to build a program which can take this and color it like this. And of course that program is built on all the work that he did to do sheep recognition. So that sheep work was completely blue skies. Microsoft was not intending to enter the agriculture industry with, you know, the killer app for sheep recognition. We did it just because it was hard, just because no one knew how to do it. We thought we'd have a go. And then it turned out that it was able to, well, let's see. So what it does is it takes every pixel in the image and decides what is that pixel's probability of being one of the 32 body parts. And the image we're seeing here is a sort of fuzzy representation because it's not going to make a hard decision for every pixel. Are you forearm, left hand and right hand can of course be confused, especially if they're on the same side of the body. So it simply returns 32 answers for each pixel saying, you know, you're definitely not a head if it's a left hand, but maybe you've got a 40% chance of being left hand, a 30% chance of being right hand, and the remaining 30% is scattered over the other categories. So we have a probabilistic picture of what's happening. And then we do the same old trick, right? We glue together this probabilistic hypotheses over time so that we can narrow it down, because the Xbox is actually only going to give you one picture, so we have to narrow it down to a single answer in the end. So let's see what it looks like. So this is what the system sees, and this is what Jamie's half of the program does. All Jamie's half of the program does is, let's look at the right hand, okay? Or, well, yeah. So its job is to color the right-hand pixels orange and not to color any other pixels orange. That's the important thing. So it gets a bit confused sometimes, only a few orange pixels. And then he's going to bring his hands over to the other side. Okay, so still even when both hands are over on that side, you can still distinguish the left and the right hand. Why? Because it's near the left elbow, etc., because everything's helping each other. If you just did hands, this would be much harder. But because he's doing all of the poses at the same time, it works better. So that was, in a sense, the key insight. Why is this cool? Because it takes every single frame completely independently and generates you a picture like this, which is roughly where the body parts are. Now, if you remember back at the start, we were talking about ideas like area, perimeter, height, as maybe a clue to what the angles were. Well, those clues are very rough. They're not going to give you a great answer. You can think of this as giving much better clues. It's now saying roughly where the left hand is, roughly where the right hand is, and then the probabilistic wrapping up of everything gives you the output. So you can look, so this is some of our early development screenshot. Here's the debug output from the body part recognizer, and then this is the register, the skeleton consistent hypothesis that is output by the system. Of course, it's not all that easy. Remember we went off to the Hollywood guys to get millions or billions of training images. Well, they came back with the millions and billions of training images. And this was our first cluster, which is very small. There are now much bigger clusters that we use to do the training, to build the system, given the training examples and given this idea. But you know, that's cloud stuff. We know how to do that. The other thing that I'd like to tell you about, to close, is that Chris and I have both been talking about probabilities, dealing with probabilities, doing the math of probabilities. And one of the things that Microsoft Research has released in the last year is a new kind of programming language, a new programming environment called infer.net, which allows you to make probabilistic programs. So the movie recommender program that Chris made, versions of the pose estimation that we have here, you can program in this new way where instead of just having numbers, so you're probably used to programs where you say x equals a plus b, and the numbers get added, probability distributions get added together and get manipulated in a way that used to be very complicated, but with this is now very simple. So with that, I would like to say thank you, and I hope you have fun with Kinect.